All right, what's up, guys? I'm trying to get everything graded and back to you, but I wanted to get a key for the Newton's Law worksheet out to you, and so you have that because there's a handful of mistakes that are pretty common. So just want you to be able to see those and hear me talk them through. Examples of Newton's first law for this first one really can be a lot of things. Some of you just gave a situation like a glass of water on a table. Sure, so something like that works. Other good examples that I saw were people saying like riding a bike and running into something and you go flying over the handlebars. So that to me is a better example of inertia, but um, anything like that works. So for the most part, those were okay. So I'm not going to type anything for that first one, but just know that ideally you can think through examples of Newton's first law. The second one says describe what inertia is. So we had that in our notes. Inertia is the tendency of an object to maintain its state of motion. So what that means, if it's at rest, it's going to stay at rest. If it's in motion, it's going to stay in motion. And that has to do with mass. So things with more mass are going to have more inertia, which then, this one a lot of people got wrong here. If we were to repeat that activity, flipping the card from under the coin, so that would be easier with the quarter because it has more mass and therefore more inertia. So the quarter is more likely to stay in place. If I'm flicking it off my thumb, the quarter would be more likely to stay there because it has more inertia. And then this, the formula for calculating weight, weight equals mass times acceleration due to gravity. So one thing that you would need for this assessment for sure. And then here in this chart, the easy way of going about this chart is you just multiply by 10 to go to the right, divide by 10 to go to the left. Some of you are kind of sticklers on using 9.8. You know, I don't have well, I do have a preference. You know, just use 10. It's just easier number wise. So I'm not sure if you've got a real love of 9.8 or not, or just why you use it. But anyway, so multiplying mass 55 times 10 acceleration due to gravity just allows me to fill these in like this, and then I would divide by 10 to go the other direction. So hopefully that's an easy calculation. And then which of these can change based on location. So that goes back to that whole inertia worksheet that we did. And so your weight changes based on your location versus your mass is always the same. So here's Newton's second law. Big idea behind this is that a net force causes objects to accelerate. And then coming from the Newton's second law lab, which I didn't make a key about because I thought it was pretty straightforward. But when the net force doubles, so one thing to remember here, I guess, let me put up here, acceleration equals net force divided by mass. So we saw those relationships in that second law lab. And so what that means is if net force doubles, then acceleration doubles. Those have a direct relationship. The net force is 5 times greater, acceleration is 5 times greater. If the net force is halved, then the acceleration is halved as well. And then here about mass and acceleration. So mass and acceleration have an inverse relationship. So if mass gets doubled, then the acceleration is halved. So it's cut in half there. Because more mass is harder to accelerate because it has more inertia. And then if the mass is 5 times greater, then acceleration is 1/5 of what it was, or 5 times less. If the mass is halved, then acceleration is 2 times greater. So that's that inverse relationship there. And so just real conceptually, you should be able to answer questions like that. 8 says, is the force of gravity on us all the same? And so we had talked about that in class because that's a really common misconception. So the acceleration due to gravity on us is always the same, but the force of gravity is not the same on us. And that's because the force of gravity on us is our weight, which is different for all of us because we all have different masses, and so then we would all weigh differently. You know, we might have a couple people who are close to the same weight, but in general, the force of gravity on us all would be different. Number 10 was probably the hardest one, and I knew it would be, and I told you that before you started, but I appreciated some of you guys making good attempts on that. So we got this person on the elevator, and I said find the net force first. So net force equals mass times acceleration. So that's Newton's second law, just rearranged algebraically. So this woman has a mass of 90 kilograms times the acceleration of 10 meters per second squared. So, oh, I'm sorry, I did that wrong. So the acceleration, for acceleration in the elevator, that was her weight I was doing, her acceleration in the elevator is 2 meters per second. So I wanted to find the net force on her. It's 90 times 2, so 180 newtons upward. So that's the net force. And so what I got to think about here is what are the forces on her? So thinking about the forces on her, what I did is I put in two vectors here, and I know she's accelerating upward, so that means that the force upward on her has got to be greater. And the net force, we just figured out, was 180 newtons. So it means there's a force downward on her, and that's her weight, that this is 900. The force upward from the elevator, it's got to be 180 newtons greater than that, because it's going to overcome that 900 Newton weight. So to figure out the upward force from the elevator, I'm going to do 180 plus 900. And that gives me my answer of 1,080 newtons. So that's the upward force from the elevator to cause, so that gives her a 180 Newton net force upward and causes her to accelerate at 2 meters per second squared. Here I've got these masses, friction-free table, so I rank them on net force. So the way some of you answered this was kind of confusing for me to know if you did it right or not. So, you know, I've got 5 to the right, 10 to the left. And each scenario has 1 to the left, 1 to the right. So you're really just subtracting those. So the net force, D is going to be the greatest because it's going to have a net force of 10 to the right, or positive 10. And D is going to be greater than all the rest of these, which all three, A, B, and C, all have a net force of 5 newtons to the right. So I would write that ranking as looking like this. So that's the way that I can understand that what you mean by your answer. So some of you just use commas, so I appreciate it if you do it like that. And then here, if I'm ranking the accelerations, so Newton's second law is acceleration is net force over mass. So I've got to do my net force divided by the mass. So like for A, net force of 5 newtons to the right divided by 5. So 5 over 5 is 1 meter per second squared. So A and C are both going to have an acceleration of 1, and B and D are going to both have an acceleration of 0.5. So then I would say A equals C, and those are greater than B equals D. Number 12, so I've got these balls traveling to the right, and it shows their position each second. So I want to rank them on the net force that causes this motion. So what we know from Newton's second law is that net force causes acceleration. So the more acceleration, the higher the net force. So I look at these and I can see that B and D are both accelerating positively, but D has moved a little bit more per second. So D would have a greater acceleration than B. C is slowing down, so it has a negative acceleration, so a negative net force. And A has a constant velocity, so a net force of 0. So we would rank 0 ahead of a negative. So then that puts my ranking looking like this. Then here, this is just used in your algebra, stuff we talked about in class on the notes to solve for each value. So acceleration, net force over mass. So this is 10 over 2 is going to be 5. 20 over 2 is going to be 10. 20 over 4 is going to be 5. Here, net force, mass times acceleration. So 2 times 5 gives me 10. Mass is going to be net force divided by acceleration. So 1, 10 over 10, and 22 over 3, which is 7.33. 13 was a little tricky for some people. So if I've got this, the friction of 5 newtons to maintain a constant speed. So that would mean that this object would have to already be moving. And if friction is 5 newtons to a constant speed or no acceleration, means I've got to have a net force of 0. So I'd have to apply a force of 5 newtons. If I want to speed that up and friction is 5 newtons, I've got to do anything greater than 5 newtons of force, because then I would have a net force causing it to speed up. If I want to decrease the speed, then I've got to have less than 5 newtons of force. So just simple like that is all I really wanted you to do. Last one really kind of depended on if you paid attention in class. And so a small car runs into a big truck, which hits with greater force. So Newton's third law says these hit with an equal and opposite force. And then which one accelerates more? So now here again is where we tie in Newton's second law with Newton's third law. And the small car will accelerate more because it has less mass. So same force, the one with less mass gets accelerated more. And then 15, we want to make really easily. Some of you made this really wrong. And so a hammer hits a nail. The reaction force to that is not what happens, to the nail or anything like that. We're thinking Newton's third law. So if object A acts on object B acts on object A, equal and opposite. So a hammer hits a nail. The reaction force to that is the nail. It's the hammer. A foot kicks a ball, means the ball, we don't have to say kick. We can just say hits the foot, which is why I hate playing soccer barefoot, because it hurts my foot when I kick it. Fist hits a face hits fist. Linebacker hits a running back, means that the running back hits the linebacker. So just equal and opposite. And so that is Newton's law worksheet, and I think that's it, right? Yep. All right.